Hello, welcome to everyone. In this video, this is our lecture number 6 of quantum mechanics. In this video, I want to discuss the Heisenberg uncertainty principle and the position measurement by gamma ray microscope and the impossible of a particle trajectory. That means a particle cannot follow the trajectory. So before that, you need to know about the previous lecture. For that, you can go through the description box. Link are given there. And in this channel, we actually discuss some physics related theoretical and some problem solution also. So if you want to watch, you can go to the description box. Separate playlist link are given there. So let's start today's discussion. That is the Heisenberg uncertainty principle. You can see this is the syllabus for University of Calcutta. This portion already discussed A and B, and this C actually covered up in this lecture number 6. Okay, and the upcoming session will be covered up in the this portion also. So let's start. So if you want to find out any position of a particle, so finding the position of particle. So finding the position of particle, position measurement of position of particle. He wants to find out the position of particle, measurement of position of particle. You know, in the microscope arrangement like that, you know, from suppose this is a microscope arrangement. This is a microscope arrangement, and in this microscope arrangement, if in this microscope arrangement, you can find out the position of any particle like here. Finding the position of any light particle like here, light comes from here to that region, and you will be find out the position. Okay, now what happened, the position of this particle, the change, this is a separation of position. This position separation or the error in position is nothing but this lambda by 2n sin theta. This is for the microscope, right? This is for microscope. Okay, so if you take the first order, that is n equals to 1, this is refractive index which is 1 for air. If you take in air, so delta x must be lambda by 2 sin theta. Lambda is the wavelength and theta is the semi vertical angle. What is the angle? This is the angle theta. This angle is theta. Okay, and lambda is the wavelength, and theta is the semi vertical angle, right? This is the semi vertical angle and this is the wavelength. Now here you can see, if you wants to find out this error, this is the delta x is the error. Delta x is the error to measure the position. So if you wants to reduce the delta x, error, you must be reduced. For delta x reduced, if lambda reduced. So if you wants to find accurate position, if you wants to find accurate position, that's mean accurate position, that is delta x tends to 0, that's mean lambda tends to 0. So you need to take lambda very much low, and you know the lowest, the lambda will be lower for gamma ray. Gamma ray is the best choice for this purpose. That's why use the gamma ray microscope to find the position of a particle. But here the but here this is not happening here. There is a position, when you reduce the position, the momentum will be changed actually. If you find out the x component of momentum, x component of momentum, if you find out the x component of momentum, that is nothing but the h nu sine theta by c, sine theta by c. H nu by c is in the relativistic mechanism. So this will be the momentum. Uh, this momentum lies between, so that one to minus h nu by c sine theta. Okay, so the change in momentum, if you write down the error in momentum, error in linear momentum, what will be the linear momentum error? That is delta px. Suppose this as a x-axis, so this is nothing but 2 h nu by c sine theta. Okay, so this is, the c by nu is lambda, so 2h by lambda sine theta. Okay, so if you take the product, that is delta x into delta px, what happened here? The delta x is nothing but the lambda by 2 sine theta. This is lambda by 2 sine theta, and delta px is the 2h sine theta by lambda. So lambda lambda 2 cancel out, sine theta cancel out, you will be get h. Okay, and which must be greater than h by 2 pi. So that's why the delta x into delta px can be written as h cross. H cross is nothing but, reduce Planck constant. H is Planck constant, and h cross is the reduced Planck constant. Okay, so these phenomena or this principle actually obtained from this experiment, that is, they want to find out the position, but when they find out the position, the momentum will be errorful, and this product will be like that. So this is nothing but actually the Heisenberg uncertainty principle. This is actually Heisenberg uncertainty principle. Uncertainty principle. Okay, so if you wants to know about Heisenberg uncertainty principle, Heisenberg uncertainty principle, you can say that is it is impossible to measure the position and momentum simultaneously. It is impossible to measure these two phenomena simultaneously. They may be position or momentum, they may be energy or electron, that is the pair. Okay, so it is the impossible it is it is impossible to measure the position and momentum or energy and time or uh, angular momentum and angular position, that is the theta. Okay, you can see this is the angular position and angular momentum. So it is impossible to measure the position and momentum simultaneously through any experiment. Simultaneously of a particle to an accuracy or accurately. Okay, accurately. So delta x into delta px is must be greater than h cross, and delta e and delta t must be greater than h cross, delta theta delta l must be greater than h cross. Okay, so this is the uncertainty principle. So it is impossible to measure two parameters simultaneously accurately, you need to sacrifice one. If you wants to measure the position accurately, then the momentum will be uncertain. This will be errorful, and if you wants to measure momentum accurately, then the position will be uncertainty. So from the conclusion, number one, if you wants to measure position accurately, accurately, then momentum measurement will be uncertain, certain, and vice versa, That's mean when you wants to measure the momentum certainly or accurately, then the position will be uncertainty. Okay, so this is the basic of Heisenberg uncertainty principle. So if you wants to prove this relation, you can easily prove this relation, that is the delta x, the position of any particle must be nearly to lambda, wavelength associated with the particle, and the de Broglie hypothesis, from de Broglie hypothesis, you can say that is the delta p momentum change is nothing but h by lambda, and lambda is nothing but h by delta x. So delta x into delta px, if you take this as px, is nearly to h, so which greater than h cross. So finally we will be get delta x into delta px is greater than h cross. Okay, now if you wants to change from momentum to energy variable, you know the energy is nothing but p square by 2m. So delta E is nothing but 2 delta P by 2m, that is the 2p delta P by 2m, and you know P is nothing but mv, P is nothing but mv by 2m delta P. So you will be get Vx delta P. This is the energy, and and this Vx is nothing but Px by m, and this is delta Px. So finally we will be get this relation, that is Px, that is V is nothing but delta x by delta t into delta Px. So delta t into delta E, so you can say delta E into delta t equals to delta x into delta Px, So you will be get these two are equals, so this must be greater than h cross. And in case of angular relation, you know the angular energy, that is E equals to half I omega square. So what will be delta E? Delta E is nothing but half I 2 omega delta omega. So you know the I omega is L, so this is L into delta omega, or you can say this is you can say that is omega, and this will be I omega. So delta omega into delta L, and omega is nothing but delta theta by delta t into delta L. So you will be get delta E into delta t equals to delta L into delta theta. So finally in three component you can say delta x into delta px, equals to delta E into delta t equals to delta L angular momentum, or delta theta into delta L equals greater than equals to h cross. This is the uncertainty principle in position. Okay, how you will find out the delta x? What will be the value of delta x? That is the uncertainty in position. Delta x is the uncertainty in position. How you will be find out it? uncertainty in position, that is nothing but the x, and this is the expectation value of x and the square. Okay, so delta x square will be like that. Okay, the expectation value of this x is the value, and this is the expectation value of x, expectation value of x. So the separation will be actually uncertainty, and the average value will be like that. This is the expectation value. So the if you expand this one, you will be get the x square minus 2 x expectation minus x expectation square plus. So this gives you the expectation of this and this expectation of this one, so this square plus this is the x expectation square. Finally you will be get x square expectation minus expectation x square. Okay, so this is the delta x square. So uncertainty of x will be nothing but x square expectation minus expectation x the square. Similarly delta px is nothing but px square expectation minus uh, px expectation square. So how the in this process you can usually find out the uncertainty principle. You can rearrange this uncertainty principle. Okay, from that you can see that is the position of the trajectory. How, if you wants to find out the trajectory of a particle, trajectory of a particle, how you will be find out the trajectory of a particle. When you wants to find out the trajectory of a particle, you know you did not find out the position accurately. You know this delta x into delta px is greater than equals to h cross. So the momentum, if you wants to personify the position, if you wants to personify the position, the momentum will be uncertainty. So the trajectory cannot be found. You can say this is the region of the path where the particle arises. So this can be like that. There will be sun position here. So you cannot say you cannot say the actual trajectory of a particle. You can say the region of the particle. Okay, so the actual path of this particle cannot be determined. You can determine the position range of the position of the particle will be find out. That is the trajectory of the particle can be find out with the range of this position. Okay, so these things actually covered, that is the uncertainty principle and the gamma ray microscope. Okay, and this illustration, and here I want to discuss more thing, that is this application of uncertainty principle. If you wants to know why the why free electron free electrons why the free electron cannot exist in a atomic nuclei, in a atomic nuclei. So if you wants to know why this free electron cannot exist atomic nuclei, you need to know that is the nucleus diameter d is the position. So the position will be d, and this is nothing but 2 into 10 to the power minus 14 meter, the range. Okay, now according to the uncertainty principle, according to uncertainty principle according to uncertainty principle, you can say that is delta px is into delta x into delta px is greater than equals to h cross. So delta px is greater than equals to h cross by delta x, and this is nothing but H cross is 1.054 10 to the power minus 34, and delta x is 2 into 10 to the power minus 14. If you find out this one, you will be get like that 0.527 10 to the power minus 20, that is kg meter second inverse. So you will be find out the this amount of minimum energy you need to find out. So P mean will be minimum momentum will be like that 0.257 10 to the power minus 20. So from a relativistic relation, that is E square equal to P square C square plus M naught square C to the power 4. So corresponding minimum energy will be like that 9.88 MeV. 9.88 MeV. But you know the that is the energy of a electron within the nucleus will be maximum up to 4 MeV. Maximum energy will be 4 MeV, right? So the maximum energy is 4 MeV, but the energy required to exist the free electron within the nucleus is 9.88 MeV. So this is impossible that is an electron can be within a nucleus. Okay. In the similar fashion, you can establish the relation, that is the Bohr radius of a hydrogen. Bohr radius of hydrogen can be established. Radius of hydrogen can be established by the uncertainty principle. That is, delta P is nothing but H cross by delta X, and delta X is nothing but the radius R. So minimum momentum is H cross by R. And the kinetic energy, what will be the kinetic energy? Kinetic energy is nothing but the P mean square by 2m mass. So this is nothing but H cross by 2m r square, and the corresponding potential energy will be minus E square by 4 pi epsilon naught epsilon by r. So total energy is nothing but kinetic energy plus potential energy. So this will be, if you added these two things, you will be finally find out that is H cross square by 2m r square minus E square by 4 pi epsilon naught r. So if you derivative this energy with respect to r in the g at this Bohr radius, this will be must be 0, and from where you will be get this relation, that is pi m square. So if you put this value, you finally get that is 5.3 10 to the power minus 11 meter. So this is nothing but the Bohr radius we actually obtained in previously. So this also explains from this experiment. So that's it for today. Thank you.